Thank you very much for having me. And today I will present a joint work with Jonathan Rohleder from the University of Stockholm. And let's get started. So first I will speak a bit about the original Calderon problem. So in this problem you have a domain and you have minus the Laplacian u plus some potential on the interior of the domain, and you have some Dirichlet boundary data on the boundary of the domain. And there you study the Dirichlet to Neumann operator, which, as the name says, it's an operator on L2 on the boundary, and it sends the Dirichlet boundary data to here the Neumann traces on the boundary. And what is then Calderon's original problem from the 80s? It is regarding the uniqueness. So if I have the Dirichlet to Neumann operator for some domain omega and for two different potentials, Q1, Q2, does this then imply that the potentials coincide? And even more, there's a question of reconstructing the potential from the Dirichlet to Neumann operator. So this is the original Calderon problem. And where does it appear? The original is in electrical impedance tomography, where the idea is to recover the conductivity of an inhomogeneous body from current and voltage measurements at the boundary, which could then be used to obtain the Dirichlet to Neumann operator. So let me now slightly go to a different area, namely the Calderon problem for so-called quantum graphs. So what is a quantum graph? So quite similar as before, we have a domain, but now the domain has this kind of graph structure. So we have vertices here, the blue and orange dots, and we also have edges connecting them. You can also think of a boundary, which are here the blue vertices or dots. In this example, they have degree 1. And we also have here the so-called interior vertices, here the orange dots. And at these interior vertices, you might have additional interface conditions. So you can think of having functions here on the edges. And on these edges, you have a differential operator. So this is what we have here. So we have minus second derivative plus some potential. So it's the same operator as before, but now on a one-dimensional spatial interval. And so here, these functions on the edges need to satisfy certain interface condition. Typically, these are the continuity Kirchhoff vertex conditions. So that means you assume that when you evaluate the functions on each edge, this should be the same value. This is the continuity, and the sum of the derivatives should be vanish. So this is a typical interface condition you consider there. And so this whole object, like the graph with the differential operators, is called a quantum graph. And here we have the same, or could formulate the same problem. So on the domain, we have this. And on the boundary, we have some Dirichlet data given. And then again, we can think of a Dirichlet to Neumann matrix, which maps the Dirichlet boundary data to the derivative here on the boundary vertices. Yeah. And one can even go beyond that. One can introduce a spectral parameter here as well. So lambda is a spectral parameter, and one can solve then this problem for every lambda, and then we get a matrix valued function here. And this kind of function has some nice properties. It's a so-called matrix valued Herklotz-Nevanlinna peak function, which is a well-studied object in operator theory. And then again, having this function, we can ask the same question as before in Calderon's problem. So here, results are known for trees. In particular, if the Dirichlet to Neumann map coincide for a tree and two potentials Q1, Q2, then it was shown by Joko and Braun and Weikart that the potentials coincide. Furthermore, there's an even stronger result, I would say, that if the Dirichlet to Neumann map coincide for two different trees and two different potentials, then we can even conclude that the trees coincide and the potentials coincide, which was shown by Avdonin and Kurasov. So now I will motivate a little bit what was our research question of the paper I will present you today. If we now neglect this dependence on a spectral parameter and go for one particular spectral value, in particular lambda equal to 0, we can ask the question, what can be determined from this Dirichlet-Neumann matrix for one particular spectral parameter? And in fact, there is no hope to recover the potential, since we fix the spectral parameter. However, we could ask, could we reconstruct the underlying metric graph, which of course has a certain distance function if you think of measuring distance between vertices and taking into account the length of the intervals. And I will directly present you our main result. And in the remainder of my talk, we will have a look how to prove that, what are the methods. So what is the main result? For trees, we can show that, as I said, set the potential equal to 0, and we can show that if the Dirichlet-Neumann matrices coincide, then also the trees, the underlying trees coincide. And even more, we have a particular formula. So if we have a tree with boundary vertices, that means the vertices which have degree 1, then we have this formula here. So here we have some technical expression, but here this is just the distance between two boundary vertices. So we have boundary vertex Vj and Vi naught, and this distance is now determined by the Dirichlet-Neumann map, but it's not the Dirichlet-Neumann map, it's some modification of it. It's a matrix which can obtained from the Dirichlet-Neumann map by setting the I naught diagonal entry to 1 and all other entries to 0. Then you take the inverse of this matrix, and here this is just a scalar product. This is the canonical unit vector, so you could say this is just a fancy way of writing the diagonal entry of this inverse matrix. So the distances between boundary vertices can be determined from Dirichlet-Neumann maps directly. And we will then see later, I will explain you a bit the details, that knowing the pairwise distances between boundary vertices of tree already determine this tree uniquely. So this is one key idea. And so this is the main result. Now I will show you how we proved this. And actually, I will leave now the quantum graph setting and go to a discrete setting, because the result we showed is in fact for discrete graphs, or discrete graph Laplacians, as they are also called. So let me briefly recall what a discrete graph Laplacian is. So you consider squared matrices, you have a graph, and on the edges you have a certain weight, WE. And then the graph Laplacian is defined like that. On the diagonal, you just sum all of the weights of all adjacent edges to a certain vertex Vi. And on the non-diagonal entries, you just set minus WE, the weight, if you have that E connects vertex Vi with vertex Vj. And you can also rewrite that, like how would it act on a vector, and then you have somehow here these, let's say, call it weighted differences here, which are summed up. And you see if you reorder the terms, you get this sum here again. So this is the discrete graph Laplacian. I think most of you know this, and it has also some nice structural properties. It is easy to see that it is a symmetric matrix, and also one can show, for example, using Gershgorin theorem, that it is a positive semi-definite matrix. And also quite interesting is that the kernel, kernel of this matrix somehow describes the connectivity of the graph in a certain sense. For example, it's known that the kernel So 0 is always an eigenvalue of the graph Laplacian. So just take the all ones vector, for instance, and you see that the dimension of the kernel is 1 if and only if the graph is connected. That means you have a path between any two vertices in a graph. So towards the Dirichlet to Neumann map for discrete graphs, let us consider the normal derivatives at the boundary vertices, which are defined in the following way. So if Vi is a boundary vertex, just consider here the sum, and somehow it resembles here the difference. Yeah, so you can really think of this like some discrete derivative. And some more notation. So towards having functions which on the discrete graph, which are prescribed by their boundary values, we consider here this potential, it's not a potential, this function phi, which is defined on the boundary vertices. And then there exists a unique function on the whole graph or the whole set of vertices, which is 0 at all interior vertices, so not the function, Laplacian applied to the function is 0 for all interior vertices. And if you evaluate this on the boundary vertices, it is precisely the function phi. And this is some notion from the literature. It is called harmonic extension of this boundary value phi. And with this, we can define the Dirichlet to Neumann map, or in fact matrix, of a discrete weighted graph. So if you consider the boundary vertices V1 to Vk, then the Dirichlet to Neumann matrix is defined by this relation. So here, for the function phi, we take the evaluation at the boundary vertices and we map that to the normal derivative. So we take Dirichlet boundary data to Neumann data. And of course, it's not hard to see that this is a linear map. And yeah, and here this U phi, as I explained, that's a harmonic extension. So in such a way, you can define the Dirichlet to Neumann map for discrete graphs as well. So what one can also easily check, I will not do it here, is that the matrix is symmetric. That's again simple, but you can also show that it is positive semi-definite, or here the terminology from operator theory, non-negative, yeah, means the same. Yeah, of course, you can also think of some special cases. So if, for example, you have only two vertices with one connecting edge, then it coincides with the Laplacian, in fact, the graph Laplacian. And if there are more boundary vertices, then something quite interesting hold. So what you can always do by resorting the vertices to split the graph Laplacian in such a way. Yeah, and here we just, as I have done it before, I consider the vertex V1 to Vk to be the boundary vertices. And here we have then just the weights of the edges at the boundary, yeah, the boundary edges. And then we have the remaining graph Laplacian, so to say. So here, these entries, this part corresponds into all other vertices which are not boundary vertices. So you can always write a graph Laplacian in such a way. Now there's a nice connection which was already observed by Curtis, Ingerman, and Morrow in '98. So in fact, this L hat matrix here is invertible. And the Dirichlet to Neumann matrix, as I have defined it previously, is equal to the Schur complement, yeah, which is here taken in this sense, yeah. So graph Dirichlet to Neumann equals D hat minus here this B transpose L hat inverse B. So there's a nice connection between the Dirichlet to Neumann matrix and the graph Laplacian, or to some extent inverses of yeah, parts or restrictions of the graph Laplacian. So that's a very important result. And remember that I want to recover this tree structure. And to do this, we will now restrict the graph to be a tree, because somehow you see that to determine the Dirichlet-Neumann matrix, I need to work with inverses of Laplacians, and that's hard for general graphs. So now we restrict to trees for this recovering procedure. Defining the Dirichlet-Neumann can, of course, be done for arbitrary graphs. So, but now I go for trees, and for the tree, I can define a natural boundary, as you have seen it before in this quantum graph picture, for instance. I take all the vertices that have degree 1 and say, this is my boundary. So now, to recover now the distances between boundary vertices, we use some nice lemma from paper by Kirkland and Shader. And to apply this, to recover the distance, I need to introduce the so-called reduced Laplacian. And for this, I take the graph Laplacian and I fix a vertex V. And what I do then is I remove a line and column which corresponds to this vertex V. And then I get a matrix which is again squared and of one dimension smaller. And then we have the following result by Kirkland and Shader. So it says that now that the inverse of this reduced Laplacian is related or can tell me the distances between two vertices. So in particular, if I consider here such a set Pij, it's a set of edges that are on both the path from Vi to V and the path from Vj to V. And V is the fixed vertex which somehow determines the reduced Laplacian. And now the entry ij of this matrix equals here the sum of the inverse weights, and I sum over all of the edges which are from the set Pij. So, and this really tells me that the entries are related to the distance between two vertices. So I spoke about equality of graphs. So let me be a little bit more precise now what we mean by that. So if we have two weighted graphs, then we can say that they're equal, or we define them to be equal if they have the same number of vertices and there exists a permutation matrix such that the graph Laplacians coincide. So you can just say you relabel the vertices, and then the graphs are equal. And for some reason, this notion is too strong. So if you want to recover graphs, because the problem basically is that we cannot distinguish between an edge and an edge where a vertex of degree 2 is located. And this is why we use a different notion. We say that two weighted graphs are equal up to vertices of degree 2, as the name says, if they are equal after removing this interior vertex of degree 2. And there's also a way of how to replace the weights. So if you have this interior vertex, you have then two weights, because you have two edges. And then you need to, when you remove the edge, you need to adjust the weight in a certain sense. And this is done by combining the inverses of the weights. And this also has some interpretation in terms of resistance, as I will show you in the following. So why is it done in such a way? So how can we now define a distance in a weighted tree? As I said, we recover the distance. This is the main idea. And from recovering distances, we can recover the tree structure. Okay, so since G is a tree, we have a unique path which connects two vertices, and then we define the distance in the following way. And this is somehow counterintuitive, because we have a certain weight, which is WE on the edges, but the distance is not the sum of the weights, but it's the sum of the inverse weights. this is the distance we will consider and which we can determine from the Dirichlet to Neumann map. And the reason somehow that for these conductivity problems, which are also considered for graphs, is that the weight is the conductivity and the inverse of the rate is the resistance. And in that sense, this distance we consider there is a well-studied object. There's this nice paper on resistance distances in graphs from 93. And in that sense, yeah, this is somehow the right distance for discrete graphs. Now, let me come to a lemma. I've mentioned it a few times already. It's somehow a well-known result, we think. So we did not include the proof in the paper, actually. We found this in a PhD thesis by Rückriemen, who did his PhD also on spectra of quantum graphs. And but again, the result has nothing to do with quantum graphs, but just with graphs. So if we consider two weighted trees with certain boundary vertices, they have the same number of boundary vertices, yeah, this is assumed. And we also assume that the pairwise distances between any two boundary vertices of the graphs coincide. Then one can show that G1 and G2, the two graphs, coincide up to vertices of degree 2. Let me briefly sketch the proof. So the idea is that you just pick two boundary vertices and we assume that there is an edge of length, the distance between the two vertices. Yeah, and somehow this in the process, this edge might be replaced by some path between the boundary vertices because actually there's no edge, but we think of it like that for the moment. So now what happens if we proceed inductively in the proof? So if we consider a third boundary vertex, you can have a look at the sketch here. The main idea is that you know by assumption all the pairwise distances here. So you know the distance from V1 to V3, V1, V2, V2, V3. And the idea is that if you know all these distances and assume that there is some point here, some additional vertex W, then you can just calculate the distance. And you can determine a unique point W just from the distances. And so you will get some star graph here. And this procedure can be repeated. So if there are even more boundary vertices, you can repeat that and you will obtain a unique graph by doing this. And this shows then that the tree is uniquely determined from noise distance of each pair of boundary vertices. Okay, that was that idea. Now I will formulate the main result for discrete graphs. So if we have a tree with a boundary again, yeah, and we have the Dirichlet to Neumann map, and then we have again this strange matrix which results from the Dirichlet to Neumann map by applying the following operation. So we replace this diagonal entry with index I0 by 1 and all other entries in the corresponding row and column by 0. This is a matrix which we call, I stick here to the notation used in the paper, it's called SI0. And then we have this formula you might recognize from the beginning of my talk. One can show that SI0 is an invertible matrix. And here, again, this is a way of writing the jth diagonal entry of this matrix. This gives you directly the distance between the two boundary vertices Vj and Vi0. So by just having this Dirichlet to Neumann map, we can compute all of these matrices as I0 for all I0 running through the boundary vertices. Then we compute the inverses, and then we then consider all of the boundary values. Then we let J run through the from I to K, yeah. And by doing that, we get then all pairwise distances between boundary vertices. And this now shows, with the previous lemma by Rückriemen, that the tree is uniquely determined from that. And so in particular, we can recover the tree structure from knowing the Dirichlet-to-Neumann matrix. The proof actually is not, it's rather simple. I would say it's maybe one page of proof, but it involves some technical calculations, which I will not show you, but I already presented you the main ideas. So let me now come back to the quantum graph case. So if we have now, I will now, in certain sense, build a bridge now back to quantum graphs, how to get the result for quantum graphs I showed you in the beginning. And if we have a graph with weights WE, then we consider the corresponding metric graph, where we now view the edges as intervals, and the length is then 1 over WE, the weights. And we can also consider then functions on this metric graph in a natural way. And typically, we are interested then in considering functions from H1, so 2 times weakly differentiable with derivatives in A2. That's a typical space, because we want to consider minus second derivative there. And we can also define the normal derivative then. So since we have here that on the edges the functions are on H2, we can consider here the derivatives. They are continuous, and we can evaluate them then on the vertices. And here it's important how to define the derivatives, but here the derivatives are taken in the direction towards the vertex. So by using this notation, now we have a function defined on gamma, our metric graph. So we can evaluate the function on the boundary vertices. And we have also here the derivatives evaluated at the boundary vertices. And we can, by doing that, we can also define a Dirichlet-to-Neumann matrix. And by considering, again, think of this construction using the harmonic extension. You can consider here functions where the second derivative vanishes on each edge, and which fulfill these standard Kirchhoff condition. That means that the sum of the derivatives is 0 at the internal vertices, and that I have continuity at the interior vertices. And it can be shown that defining the Dirichlet-to-Neumann matrix like that is works out quite well. And this is done in this book here. It's the Introduction to Quantum Graphs from 2013. That's quite a good reference for quantum graphs. So finally, now from the MG, so the Dirichlet-to-Neumann from discrete graph to the one for the quantum graph. So if we consider now a function which is harmonic on every edge, so second derivative vanishes and satisfies this continuity Kirchhoff conditions at the interior vertices, then we can somehow, it is clear that since the second derivative vanishes, that f is a linear function each edge, and then we can write it like that. It's a linear function, and one can then compute the derivative, and by doing that, we see that. So if you consider these u's which arise from the restriction of this function f on the metric graph, then I recover this formula. So Laplacian applied to this is then just sum of the derivatives here, and it's also 0 on the interior vertices. And this was just the definition of the Dirichlet-to-Neumann map for discrete graph. So in fact, by using this construction here, we see that both Dirichlet-to-Neumann maps or matrices coincide. And in this sense, we have now seen, by using now our main result on discrete graphs, that also knowing the Dirichlet-Neumann map of a quantum graph determines the tree uniquely. Okay, let's have a look at two examples. The first example is, both examples show in a certain sense that the results are sharp in a certain sense. In the first example, the main message is that cycles cannot be detected from the Dirichlet-Neumann map. That means if we consider two graphs here, G1, where this one contains a cycle and the other one's just a star graph, and you choose the weights or the length of the edges in a certain way, namely here I choose 1 for all, and here in G2 I choose it slightly larger, and one can show that the Dirichlet-Neumann maps coincide for these two graphs, yeah, and we can just do the calculations if you like. So first of all, you would consider here the graph Laplacian, the discrete one, by our labeling. If you remember, the first entries are the boundary vertices. So we have here 1, 1, 1 as a degree, and we have 3 interior vertices, which are these 3 vertices, and they all have degree 3. And since the weight is 1, so you sum all the weights, and the other entries are then, so you get 3 here on the diagonal, and the other entries are here in the -1. So this is the Laplacian, discrete graph Laplacian. And as I showed you, there is this result on the how to obtain a Dirichlet-Neumann map directly just by using the Schur complement. And if you calculate this, it's not hard to calculate here this inverse matrix, you will end up with such a matrix, yeah? So, okay, so this is the first graph. Let us look at the second graph. You can do the same, it's a star graph. So again, you have 3 boundary vertices. So on the graph Laplacian, we have this one. Yeah, this is the weight. And since there's only one edge, you have directly this weight here. And there's this one center vertex, the interior vertex, which is connected to all boundary vertices. So this is, again, a graph Laplacian. Again, you can apply a Schur complement. Here, inverting this entry is much easier. Yeah, and so you might not remember the matrix from the last slide, but it's easy to check that, in fact, this is this matrix again, so both coincide. And by that, we see that the Dirichlet-Neumann matrix alone does not determine the graph uniquely if we have cycles. So we cannot get more information from this Dirichlet-Neumann matrix for this one particular spectral value. Yeah? Furthermore, if I have only partial boundary data available, then this does also not determine the tree structure, which is also not surprising, I would say. So in particular, we consider here 2 graphs. So you can think of this as having the graph G1, so again a 3-star, and then just you remove one boundary vertex, so then you have only one edge left, which is the graph G2. Again, you choose the edge length or weights in a suitable way, and you can see then that if you restrict only to a certain number of entries in a Dirichlet-Neumann map, then you cannot tell if it's the larger graph or if it's this graph. So, but I will show you the calculations. So the graph Laplacian, we have seen this in the previous example. That's quite clear. And for this one, it's only you only have one edge, yeah, 2 vertices, and this is given by that, yeah. So it remains to compute the restriction of this Dirichlet-Neumann map. So this is done now on this slide. So if I consider now the Dirichlet-Neumann matrix only with respect to 2 boundary vertices, then I get this formula. So here again, the diagonal entries, then inverse then of the remaining 2 vertices, and I arrive precisely at the same Dirichlet-Neumann map as for the graph, which consists only of one edge. Yeah, so it was MG2. This shows that, as I said, partial knowledge of the Dirichlet-Neumann matrix does not uniquely determine the tree. And I'm already at the end of my talk, so here is a list of references on the subject. So I just sorted them alphabetically. There is a lot of work which was done already in the 90s by Curtis and Morrow, who also study Dirichlet-Neumann maps. There's also quite interesting in the quantum graph case. There's this recent book by Pavel Kurasov on spectral geometry of graphs, who also studies this inverse problem I showed you for quantum graphs. And it's also nice that it is open access. And furthermore, there's this reference by Ullmann. If you're more interested in the Calderon problem, he summarizes 30 years of the Calderon problem. So a very valuable reference. And also there has been really recent work here, how to recover conductances on not tree graphs, but so-called spider networks. Yeah, so there's a lot of research going on there. And with that, I would like to thank you for listening, and I'm open for questions.